The most sophisticated, most expensive, and technically complex vessel of its time. Atomic power. Invulnerable armor. The pride of a nation destined to rule the oceans. And then, she vanishes. Without warning, without a fight, in a fraction of a second. For decades, official reports remained dry and clinical. But what actually happened to the USS Thresher is more terrifying than any military engagement. It wasn't an enemy attack. It was a rebellion of the laws of physics against human hubris. How did the world's newest technology turn against its creators? Why did the very rescue system designed to bring them to the surface become the cause of the catastrophe? And what monstrous force is capable of crushing 8,000 tons of high-strength steel, like a paper cup, faster than you can blink? Today, we examine the story of the United States Navy's nuclear submarine, the USS Thresher. We will uncover details that engineers kept silent about. We will break down, second by second, how water turned into fire and ice blocked the air. You will see how one tiny penny-sized mistake made on shore can destroy a multi-million-dollar project at the bottom of the ocean. No conspiracy theories, just the unsettling facts. Be sure to watch until the end. The resolution of this story and the Commission's findings changed the rules of submarine warfare forever. April 10th, 1963. Morning. The U.S. Navy rescue ship Skylark drifts slowly in the cold waters of the North Atlantic, about 350 kilometers off the coast of Massachusetts. Outside, a biting wind blows, but the acoustic station is warm, smelling of strong Navy coffee. Officers huddle around the speaker of the UQC underwater telephone, nicknamed Gertrude. Directly beneath them, in the pitch-black darkness of the ocean, lies the Thresher, the newest, most expensive, and technologically advanced nuclear attack submarine in the United States. She is performing a series of test dives. According to the plan, the sub descends in 30-meter increments. Right now, she's approached her maximum test depth, 360 meters. At this depth, the ocean stops behaving like normal water. It turns into a heavy, crushing mass. The pressure reaches 40 kilograms for every square centimeter of the hull. The ship's frame literally groans under the strain. The clock strikes 9:12 a.m. The Gertrude speaker suddenly crackles to life. Through the thickness of the water and heavy static, a distorted voice breaks through. Most likely, it is the sub's commander, Lieutenant Commander John Harvey. His tone is calm, as regulations demand, but the words themselves make the watch officer on the surface hold his breath. Experiencing minor difficulties. Have a positive up angle. Attempting to blow, the connection cuts off with a loud hiss. The officers on the Skylark exchange glances. The phrase, minor difficulties at maximum depth, is a dangerous illusion. When you have 360 meters of freezing water above you, any minor problem can escalate into a catastrophe in seconds. A positive up angle meant the 8,000-ton steel machine had begun to tilt backward. She was getting heavy, losing momentum, and slowly sliding stern first into the abyss. At 9:13 a.m., the sonar technician on the Skylark presses his headphones back to his ears. "Thresher, this is Skylark. Providing my coordinates. Report your condition." The only response is the rhythmic noise of the ocean. 4 long minutes pass. And then, at 9:17 a.m., the sonar tech hears a sound that will haunt him for the rest of his life. It wasn't the roar of a magazine explosion or the hum of a reactor. It was a low, visceral crunch. The screech of high-strength steel being shredded. Imagine the sound of an empty aluminum can being instantly crushed in a fist. Now, multiply that sound by the scale of a 100-meter ship. It was the sound of implosion. The instantaneous collapse of the pressure hull. The Skylark's navigator grips the microphone until his knuckles turn white. "Thresher, answer. Thresher, do you hear me?" There was no answer. In that fraction of a second, 129 men remained on the bottom of the Atlantic forever. To understand how the pride of the U.S. Navy turned into a twisted mass grave, we need to rewind time. Back to the moment this submarine was being designed, promising to be the invincible weapon of a new era. The late 50s. The Cold War is at its peak. The Soviet Union is actively building up its submarine fleet, and the US Navy Command needs a symmetrical, or better yet, superior, response. They need the perfect underwater hunter. Until this point, most submarines were essentially surface ships that could only temporarily go underwater. Diesel-electric boats of the World War II era needed oxygen. They had to surface to charge batteries, exposing their silhouette to enemy radar. But Project 593, named Thresher, changed the rules forever. This wasn't just a new class of submarine, it was a leap into the future. A smooth, teardrop-shaped hull based on the revolutionary albacore concept. And most importantly, an S-5W nuclear reactor at the heart of the ship. It gave her infinite energy. Now, the sub could stay underwater for months, limited only by food supplies and crew endurance. But to become a true predator, the Thresher needed eyes and ears. Engineers took an unprecedented step. The entire bow of the submarine was occupied by a giant spherical BQQ-2 sonar station. It was so massive that the torpedo tubes had to be moved to the middle of the hull and angled outward. The Thresher could hear an enemy tens of kilometers away while remaining absolutely silent. Command of this technical marvel was entrusted to 37-year-old Lieutenant Commander John Harvey. An experienced officer, he had passed the rigorous school of Admiral Rickover, the father of the American nuclear fleet. Harvey knew his ship down to the last screw, and he knew the Thresher's main advantage was her armor. The sub's pressure hull was welded from the newest HY80 alloy. This was high-strength steel, capable of withstanding colossal compression loads. Thanks to this, the Thresher could dive to depths unreachable by any Soviet submarine of the time. The official operating depth was classified, but the calculated test depth was 396 meters. It seemed this multi-ton steel leviathan was invulnerable. But here is what only a few engineers knew back then. In the race to meet assembly deadlines during the arms race, the Pentagon approved one fatal compromise. Inside the Thresher's pressure hull ran miles of piping. Through some of these pipes circulated freezing seawater, necessary for cooling the nuclear reactor's systems. These pipes were under the same monstrous pressure as the sub's outer hull. However, instead of welding the joints of these pipes permanently, the shipbuilders used silver brazing. It was faster, it was cheaper, and it created over 3,000 potential vulnerabilities scattered throughout the submarine's circulatory system. Each of these silver brazed joints was a ticking time bomb, 3,000 blind spots in a perfect killing machine. Harvey and his crew of 128 believed in their ship. They spent several months at the Portsmouth Naval Shipyard while the boat underwent scheduled repairs and modernization. Now, it was time to test the updated systems in action. On the morning of April 9, 1963, the Thresher cast off. They were heading into the ocean to conduct a series of routine deep-sea tests. No one on the pier knew they were saying goodbye forever. The Portsmouth shipyard was damp and cool. John Harvey climbed onto the bridge of his boat. Behind him followed the crew, as well as 17 civilian specialists and engineers. These men were there to monitor the Thresher's systems after the lengthy overhaul. With the crew, there were 129 people on board. For such a boat, it was a full house. Escorted by two tugs, the 100-meter black hull slowly pulled away from the pier and set a course for the open ocean. Ahead lay the Gulf of Maine. Their task was a series of trials known in the Navy as post-overhaul sea trials. The most critical stage was testing the hull's integrity and system reliability at maximum diving depth. For this mission, they were accompanied by a surface support vessel. The submarine rescue ship Skylark, hull number ASR-20. Skylark was not a combat ship. It was a slow, aging vessel whose main task was to listen to the ocean and, in case of emergency, provide aid to the submariners. It carried a diving bell. But here lay a dark irony. The Skylark's diving bell could only descend to a maximum of 250 meters. The Thresher was planning to dive to nearly 400. If the boat hit the bottom beyond those 250 meters, the rescuers on the surface would become mere spectators. They wouldn't be able to help. Harvey and his men understood this perfectly. Such were the rules of the game in the submarine fleet. On the first day of trials, everything went according to plan. The Thresher performed a series of shallow dives. The crew checked the rudders, the trim, and the reactor's operation at low depth. The boat responded to commands like a disciplined beast. The radio messages sent back to base were short and dry. Systems operating normally, preparing for the deep water phase. Harvey's plan was strict and methodical. They weren't going to dive to 400 meters in one go. The descent was to be stepwise. The sub would drop 30 meters, then stabilize. The crew would check the hull for leaks, listen for noises in the compartments, and ensure no pipes were spraying water. If everything was in order, the boat would descend another 30 meters, and so on until they reached the bottom of their test zone. Every 15 minutes, the Thresher was required to check in with the Skylark via underwater telephone. This protocol was written in blood. As long as Harvey's voice sounded in the surface vessel's speaker, everything was fine. The night of April 10th was spent in preparation. The sub was at coordinates that would later be etched into naval history books. The ocean depth in this area was a staggering 2,500 meters. Under the Thresher's keel yawned a black, frozen abyss. At dawn, at 7:47 a.m., Harvey gave the order to begin the main test. On the bridge, the hatches were secured. Ventilation valves were closed. The main ballast tanks took on water, and the boat, settling heavily, slipped beneath the Atlantic waves. At 7:52 a.m., the Skylark received the first message. Skylark, this is Thresher. Depth 120 meters. Checking integrity. The officers on the surface ship drank coffee and kept the logbooks. So far, everything was on schedule. But as the depth gauge needle on the submarine crawled downward, the physics around them began to change. With every 10 meters, the pressure increased by 1 full atmosphere. What was once just numbers in an engineer's calculation became a ruthless, crushing force at 300 meters. The HY-80 steel began to compress. By 8:53 a.m. on April 10th, the depth gauge on the Thresher passed the 300-meter mark. The boat continued its descent into total darkness. At this depth, sunlight no longer exists. The water temperature outside drops to near 0 degrees Celsius, and the pressure becomes so colossal that even the high-strength HY-80 steel begins to deform. This is not a metaphor. The physics of the process are such that a 100-meter submarine hull under such pressure actually shrinks. Its length decreases by several centimeters. Imagine that sound, a hollow, metallic groan echoing through the narrow corridors of the boat, the creaking of bulkheads, the snapping of deck plating. For submariners undergoing their first deep-sea trials, this sound might seem like a symphony of impending death. But for John Harvey's experienced crew, it was just the music of their work. The steel was breathing, resisting the ocean. Inside the boat, it was still warm. The S-5W nuclear reactor hummed, fans whirred, and officers spoke in calm, quiet voices. In the control room, the dim light of the instruments glowed. The Thresher was supposed to descend to 396 meters, its test depth. At 9:02 a.m., the Skylark on the surface receives another message via the UQC Gertrude. Course 090, proceeding to test depth. The surface ship, rocking on the Atlantic waves, confirms receipt. The officers on the Skylark's bridge watch the stopwatch. By protocol, the Thresher must check in every 15 minutes, but at maximum depths, they try to communicate more often. So the sonar techs on the surface know the boat is alive. At 9:09 a.m., Harvey reports, reached half of test depth. This meant they had passed the most dangerous threshold after 300 meters. The external pressure was now nearly 40 kilograms per square centimeter. If a hole the size of a pencil were to form in the pressure hole at this depth, Water at 40 atmospheres would blast inside at the speed of a bullet. This jet would be powerful enough to cut a human in half, and no emergency patch could stop it. At 9:12 a.m., the Gertrude speaker on the Skylark suddenly emits a loud click. Underwater telephone communication is often accompanied by heavy static. Sound waves distort in the water column, especially with changes in temperature and density. But what the Skylark's sonar tech heard made him freeze. A voice broke through the crackle. It wasn't panicked, but there was a palpable tension in it. Experiencing minor difficulties, have a positive up angle, attempting to blow. And then, a loud whistling sound of compressed air. And silence. The officers on the Skylark immediately realized that the words minor difficulties were Captain Harvey's attempt to stay calm on the air. A positive up angle meant the sub's bow was tilting up, while the heavy stern was sinking. The boat was losing its horizontal trim. Worse, the words attempting to blow meant Harvey had ordered high-pressure air to be forced into the main ballast tanks to emergency expel the water and surface. It was a gesture of desperation. It was an emergency alarm. But why did the newest nuclear submarine, with a powerful reactor, suddenly start sinking stern first? What forced Harvey to order an emergency blow? To understand exactly what happened at 9:12 a.m. at a depth of nearly 400 meters, we must transport ourselves inside the Thresher's pressure hull, into the stern. That's where the engine room and the heart of the submarine, the S5W nuclear reactor, were located. Unlike diesel boats, a nuclear submarine doesn't just float in water. It lives because of water. To cool the reactor and condense the steam that turns the turbines, the boat constantly pulls in thousands of liters of ocean water through sea chests. This water circulates through a massive system of piping inside the pressure hull. And remember the pressure this water was under at test depth: 40 atmospheres. 40 kilograms on every square centimeter of pipe. Now remember that fatal compromise by the engineers: silver brazing instead of rigid welding. At 9:12 a.m., one of those silver joints failed. No one knows exactly where the crack formed, but the most likely scenario is this. A breach occurred in the seawater cooling system in the engine room. At first, it was just a whistle. A thin, barely noticeable stream of water under monstrous pressure shot out of the failed joint. But silver brazing is treacherous. Once the joint weakens, the water begins to rip it apart with geometric progression. In seconds, the thin stream turned into a roaring, uncontrollable torrent. A jet several centimeters thick was hitting with such force that it could punch through bulkheads and strip the metal casing off equipment. Freezing Atlantic water roared into the sub's aft compartment. Water weighs a ton per cubic meter. As this weight rapidly accumulated in the stern, the 100-meter submarine's balance was destroyed. The stern began to get heavy, inexorably sinking. This caused the positive up angle Harvey reported to the surface. But the leak itself, even one this severe, wasn't yet a death sentence. The crew had pumps capable of moving water and watertight bulkheads to isolate the flooded compartment. The true catastrophe occurred because of where the water hit. The powerful jet of seawater struck directly into the reactor's electrical control panels. This caused a massive short circuit. Showers of sparks, the smell of burning insulation, and an instant loss of power to the main panels. This is where the automation designed to protect the boat instead killed it. The S5W nuclear reactor was designed so that at any critical electrical failure or threat of overheating, it would immediately shut down. This is called a reactor scram. Control rods drop into the core, the chain reaction stops, and steam production ceases. The Thresher's reactor stopped. The turbines stopped receiving steam. The main propeller shafts stopped turning. The boat completely lost propulsion. For a submarine with a heavy stern, losing propulsion at maximum depth is a disaster. As long as the screws were turning, Harvey could have gone full speed ahead and tried to pull the heavy boat to the surface using the hydrodynamics of the diving planes. But now, the Thresher was just an 8,000-ton steel slug, tilting onto its tail and sliding into the abyss. In the control room, emergency sirens wailed. Commander John Harvey made the only logical decision. He ordered an emergency blow of the main ballast tanks. This is the most radical maneuver. Compressed air from the sub's storage flasks is forced into the water-filled ballast tanks at colossal pressure. The air is supposed to push the water out, drastically increasing the submarine's buoyancy and popping it to the surface like a cork. This sound, the loud, whistling roar of the blow, is what the Skylark heard at 9:12 a.m. Harvey pulled the levers. High-pressure air rushed through the pipes toward the ballast tank valves. It seemed salvation was at hand. The boat should have shuddered and begun its ascent. But the roar of air suddenly cuts off. Instead of the life-saving expulsion of water, there is a ghostly, unnatural silence, broken only by the groan of the ocean outside and the shouted reports from the aft compartment. The boat does not rise. It continues to fall. What happened? The answer lies in the ruthless laws of thermodynamics, specifically the Joule-Thomson effect. Let's look at the physics. The air in a submarine's flasks is stored at incredible pressure, about 300 atmospheres. This is necessary to fit a massive volume of air into the limited space of steel cylinders. When Harvey gave the order to blow, the valves opened, and this compressed air rushed into the piping. But in the path of this air stood reduction valves, narrow bottlenecks that lowered the air pressure to working levels. And this is where the Joule-Thomson effect struck. According to the laws of physics, when a gas under very high pressure suddenly expands while passing through a narrow opening, it cools down rapidly. And this cooling isn't just noticeable, it is extreme. The moment the high-pressure air burst out of the Thresher's flasks and passed through the reduction valves, its temperature plummeted. The air pumped into the submarine's flasks by shore compressors is never 100% dry. It always contains a microscopic amount of moisture. During the overhaul at Portsmouth, a bit more moisture than usual had entered the system. And when the compressed air, containing these microscopic water droplets, passed through the valves and instantly cooled to sub-zero temperatures, the moisture turned into ice. In fractions of a second, ice plugs completely blocked the reduction valves. The life-saving air that was supposed to push the water out and save the Thresher was trapped in the pipes. The emergency surfacing system had choked on its own ice. In the control room, the crew realized the horror of the situation. The sound of the blow had stopped, but the boat hadn't gotten a gram lighter. On the contrary, with every second, the breach in the stern took in more water. The depth gauge needle crawled downward, passing 330 meters, 350 meters. Harvey had one more theoretical chance: restart the reactor. But the S5W safety protocols were unyielding. After an emergency scram, restarting the nuclear plant took tens of minutes. The process required the gradual withdrawal of control rods and the warming of the loops. The Thresher didn't have minutes. It had seconds. At 9:13 a.m., as the Skylark sonar tech tried to hail the boat, hell reigned on board the sub. Men in the engine room were knee-deep in freezing water, fruitlessly trying to manually close the ruptured pipe, fighting a jet hitting with the force of an industrial press. In the control room, officers shouted orders, trying to reroute the remaining air around the frozen valves. But the physics were final. The 8,000-ton steel tube, devoid of propulsion and buoyancy, with its bow up and its stern flooded, crossed its critical limit. It was falling past its maximum collapse depth. Somewhere below, in the pitch-black ocean, lay the boundary where HY-80 steel could no longer resist. The boundary where the water would take what was hers. The clock shows 9:14 a.m. The submarine Thresher has no power, no propulsion, and is slowly, inexorably, sinking stern first. Inside the pressure hull, 129 men are fighting a hopeless battle. The depth gauge crosses 396 meters, the sub's calculated test depth. Here, the territory of engineers ends, and the territory of pure, destructive physics begins. The water pressure outside reaches 40.5 atmospheres. For every square meter of the sub's steel skin, there is now a weight equal to the mass of 400 passenger cars. The HY-80 steel hull, which at shallower depths only groaned and creaked, now begins to deform. Imagine the submarine not as a monolithic piece of metal, but as a hollow cigar, struggling with its last strength to hold back the ocean. The steel ribs, the frames, begin to buckle. The pressure hull compresses so tightly that the paint on the inside walls begins to crack and flake off in tiny chips. In the control room, the sounds become deafening. It's no longer creaking, it's the sound of metal tearing. At 9:16 a.m., the depth reaches approximately 450 meters. Pressure, 45 atmospheres. At this moment, most likely, the internal watertight bulkheads are the first to fail. The aft compartment is already half full. Tons of water accumulate in the stern, and the boat assumes a nearly vertical position. The up angle becomes so steep that unfastened equipment, tools, and people fall toward the engine room. But the most terrifying thing happens at 9:17 a.m. At a depth of about 480 meters, the Thresher's pressure hull reaches its elastic limit. The steel can no longer hold back the ocean. Implosion occurs. We are used to the word explosion, where energy moves from the inside out. An implosion is an explosion in reverse. It is the instantaneous, catastrophic collapse of a hollow object under colossal external pressure. When the pressure hull gave way, it didn't happen gradually. At one point, the steel buckled inward. As soon as the perfect cylindrical shape was compromised, the hull's strength instantly dropped to zero. In the next 20th of a second, the ocean collapsed into the boat. Water rushed into the compartments at a speed exceeding the speed of sound. But before this wall of water reached the people, something even more horrifying happened. A phenomenon physicists call the diesel effect. Remember how a diesel engine works? A piston sharply compresses the fuel-air mixture, causing its temperature to instantly rise to thousands of degrees, leading to self-ignition. The same thing happened inside the Thresher. 100 meters of air were compressed by the rushing water in a fraction of a second. The volume of air shrank dozens of times faster than you can blink. According to the laws of thermodynamics, when a gas is compressed at such incredible speed, its temperature jumps to astronomical levels. At the moment the Thresher's hull collapsed, the air inside the boat instantly heated to the temperature of the surface of the sun. The air itself became a flash of flame. All combustible materials in the compartments ignited instantly. The crew didn't have time to drown. They didn't even have time to realize the boat was failing. A thousandth of a second before they were hit by a wall of water moving like a bullet, they were at the epicenter of a fiery inferno. And then the ocean finished the job. The supersonic impact of water tore the 100-meter steel Leviathan into thousands of pieces. Heavy machinery, the reactor, and the remains of the hull continued their fall into the abyss, scattering over a massive area. The propeller, ripped from its shaft, acted as a grim stabilizer for the severed stern section, which spun as it dove nose first toward the bottom. The whole thing took less than a second. At a depth of 2,500 meters, the scattered debris settled into the soft silt of the North Atlantic. The ocean closed over the grave of 129 men. Back on the Skylark, it's 9:17 a.m. On the surface of the ocean, nothing unusual is happening. The weather is calm, a light breeze is blowing. Waves rhythmically lap against the side of the surface ship. Inside the Skylark's acoustic shack, the atmosphere is entirely different. The navigator squeezes the microphone. "Thresher, this is Skylark. Answer." Only static crackles in the speakers. The sonar tech, an experienced sailor, presses the headphones so hard his ears turn red. He is trying to isolate any sound from the background noise of the ocean. At 9:17 and 15 seconds, the tech flinches. He doesn't hear words. He hears a low-frequency, guttural sound. It's like the sound of a giant metal shipping container being instantly crushed by an invisible hand. The sound lasts less than a second, but it is so loud it is registered even by seismic stations on the coast. Everyone on the Skylark freezes. The captain of the rescue ship orders signaling grenades to be dropped immediately. It's a standard protocol. "Surface immediately, you have trouble." One by one, sailors drop small metal cylinders overboard. Bang, bang, bang. Dull explosions echo underwater. On the Skylark, silence returns. Men stare at the water, expecting the black sail of the Thresher to come crashing through the surface at any moment. 10 minutes pass. 30 minutes. the surface of the ocean remains perfectly still. At 11:04 a.m., the captain of the Skylark realizes the obvious cannot be denied. He orders the radio man to tap out the message. Contact with Submarine 593 lost. Attempts to establish contact unsuccessful. Heard sound resembling implosion. This message triggers a chain reaction all the way to the top of the Pentagon. Patrol planes take to the air. By evening, an entire armada converges on the search area. But on the surface, there is nothing. Only late into the night does one of the destroyers report finding a small oil slick and several pieces of yellow plastic. These were pieces of the Thresher's internal insulation, and they were charred. These very pieces would confirm the theory of the diesel effect, the instantaneous combustion of air. By the morning of April 11, 1963, the U.S. Navy officially declares the submarine lost. America is in shock. It was the world's first nuclear submarine catastrophe. And the most frightening part, no one understood why. Rumors of sabotage, Soviet torpedoes, and reactor explosions began to circulate in the press. To prevent panic, the U.S. Navy created a special court of inquiry to investigate the causes of the catastrophe. It was led by Vice Admiral Bernard Austin. Austin's commission had one massive problem. They had zero physical evidence. Investigating the loss of a submarine at a depth of 2,500 meters was like trying to solve a murder in a locked room without a key. Austin's commission formulated 5 main hypotheses. Hypothesis 1, sabotage. But sonar hadn't detected any other propellers, and Harvey had reported internal difficulties. Hypothesis 2, reactor explosion. But reactors of this type don't detonate, and water samples show no radiation. Hypothesis 3, crew error. But the Thresher had been diving methodically under the control of an experienced captain. Hypothesis 4, loss of buoyancy. Here, experts turn their attention to the Joule-Thomson effect. Shoreside experiments showed that valves froze solid in seconds. The last hypothesis tied everything together: structural defects. The commission dug through documents and found that silver brazing had been used instead of welding during repairs. At test depth, those silver joints turned into a death trap. Admiral Austin reached his verdict. A silver brazed pipe had ruptured in the engine room. The jet hit the electrical panels, the reactor scrammed, and the boat lost propulsion. The attempt to blow the ballast failed because of ice in the valves. Powerless and heavy, the boat fell into the abyss. It was a verdict that blamed the system and its compromises. But for this conclusion to become the truth, they had to find the boat itself. In the summer of 1963, the bathyscaphe Trieste arrived in the search area. The ocean reluctantly gave up its secrets. The bathyscaphe descended to the bottom, moving at the speed of a pedestrian. The first dives yielded nothing. But then, in a beam of light, metal glinted. It was a debris field. What the Trieste pilots saw on the bottom finally confirmed the implosion theory. Mangled metal lay across a vast area. The 100-meter pride of the fleet had been shredded into thousands of fragments. The pilots found a piece of pipe with the marking 593. But the pressure hull itself was gone. It had ceased to exist the moment the pressure crushed it. Photos from 2,500 meters deep went around the world. They became a lesson that the ocean does not forgive haste. The loss of the Thresher led to the creation of the SubSafe program. It was a set of the strictest rules. The Navy banned silver brazing in critical systems. Now, only welding and X-ray inspections were allowed. Ballast blow systems were completely redesigned, so the ice trap would never close again. The statistics speak for themselves. Before SubSafe, the U.S. Navy lost 16 submarines in non-combat conditions. Since the program was implemented in 1963, not a single SubSafe certified submarine has been lost. John Harvey and his crew did not return from that voyage. Their boat became the first loss of the atomic era. But their deaths were not in vain. The lesson, written at the bottom of the ocean in crushed metal, saved thousands of lives. The ocean remains a ruthless environment. It does not forgive mistakes. And every time a modern submarine heads into the deep, the crew knows they are safe only because of that terrible morning of April 10th, 1963. The morning the ocean claimed the Thresher.